Thank you, everyone, for attending today's webinar, What's New in 3D Printing Materials. I'm Leslie Langnaw, Managing Editor at Design World Magazine, and I'll be your presenter today. A quick background of me. I have a Bachelor of Science degree in Mechanical Engineering from Michigan State University, and I've been reporting on 3D printing additive manufacturing for about 8 years with Design World Magazine. Just a couple of housekeeping details before we get started. You will see several boxes on your desktop, all of which can be moved around to suit your preferences. For more information on any of the companies mentioned in this webinar, check the Additional Resources box, which is initially located at the lower right-hand corner of your desktop. We also have a tweet box on the desktop, so feel free to tweet any interesting points right from there. There's a list of hashtags for you to use. So let's get started. Materials are a critical component in any 3D printing additive manufacturing process, and the additive industry is focused on developing materials for these processes. The trend lately is to take advantage of chemistry and develop materials you can't find naturally because many additive processes let you create new materials that may more nearly meet a specific design or end-use need. It's easy to take a metal and grind it up into a fine powder and use that. But what if you can add other alloys to that powder and come up with an even more amazing material? This is what some developers are doing. The materials I'm going to go over are those that have been introduced in just the last 2 to 3 months. More were introduced at the beginning of this year, so this is a very vibrant field right now. There are 3 major areas of development that I will cover: high temperature, strength, and materials for medical applications. Plastics first. The high temperature reference with the new plastic materials refers to either the plastics can handle the high temperatures of an additive process or the end-use parts will withstand applications involving high temperatures. These materials have other features, of course, but the vendors are emphasizing a high temperature as a key feature. Solvay is a source of a number of high-temperature polymers for additive manufacturing. These include PEEK, PEI, which is also known as Ultem, and PPSU. They're a group of polymers that handle high temperatures, having a glass transition temperature of about 218 Celsius. They also resist creep and work well for applications that require sterilization. A number of additive vendors and additive service providers work with these materials. At the recent Rapid Show, SABIC introduced a number of new materials. Now, SABIC has a relationship with Stratasys, so many of these materials work well with the Stratus Fortis systems, but they can be processed with other systems too. SABIC is working on a polycarbonate material that can be used on selective laser sintering machines. Tests are indicating that these PC materials display good mechanical properties and have part densities above 96%. SABIC says that these materials may provide an alternative to polyamide 12 and can be processed using commercially available printers. You can see a little bit of information about their properties to the very right of this graph here. Most polycarbonate materials soften and become more flexible at temperatures above 150 C, which is their typical glass transition temperature. The chemical bond of polycarbonates makes them stiff and impact resistant below this temperature. SABIC offers XTEM polyamide filaments for extrusion systems, particularly Stratasys fused deposition modeling systems. What you see in the photo is what was introduced at the Rapid Show. These filaments are suitable for applications involving temperatures higher than the Ultem PEI filaments because they have a glass transition temperature of 311 C and will resist creep at to 230 C. They have demonstrated long-term heat resistance. XTEM PEI is based on the Ultem PEI resin, a Cycolac ABS resin, and Lexan polycarbonate resins. They have the same composition as SABIC's injection molding grades. The Ultem PEI filament handles applications that require high heat resistance, high strength, and low flame, smoke, and toxicity. SABIC's Ultem AM9085F filament is a high-performance polyethythermide product manufactured from Ultem 9085 resin. It offers heat resistance to 165 C and mechanical strength. It is UL94VO compliant at 1.5 and 3.0 millimeters and meets FAR 25.853 and OSU 65/65 requirements with low flame, smoke, and toxicity. It is available in black and non-pigmented colors. Lexan AM1110F filament is a general-purpose polycarbonate material manufactured from Lexan HF1110 resin. It has thermal properties higher than those of general-purpose ABS filaments, is UL94V2 compliant at 3.0 millimeters, and is available in white. EnvisionTech offers ECE. It's a cyan ester and is a stiff, heat, and chemical-resistant material. It is comparable to other cyan-type ester materials in the 3D printing market. It softens at temperatures higher than 170 degrees C, making it suitable for applications that require thermal stability, such as electronic encasements and under-the-hood parts. It is compatible with EnvisionTech's desktop and per factory machines. DSM Somos introduced Somos Taurus at the Additive Manufacturing Users Group Conference this year. Somos Taurus is the latest addition to the Somos stereolithography material portfolio and is geared for objects that must perform in high temperatures. This material is durable and has a heat deflection temperature of 95 degrees Celsius or 203 degrees Fahrenheit, which means that the parts will start to bend under load at this temperature. The material is charcoal gray in appearance, giving it the look and feel of traditional thermoplastics. In addition, Somos claims it is easy to process, clean, and creates parts with smooth surfaces, fine features, and details. Somos Taurus is the first of several stereolithography materials to come from Somos that combine the toughness and temperature features suitable for end-use applications. And just as an aside here, heat distortion temperature and glass transition temperature are often viewed as being the same, but they're not necessarily so. Both terms indicate when a material, usually a plastic, will soften or deform at a specific temperature. Heat distortion temperature, though, usually adds a factor of underload. Ceramax from 3D Systems is a ceramic reinforced composite, which of course would have good temperature, chemical, moisture, and abrasion-resistant characteristics. It is for the 3D Systems Pro X800 system. The glass transition temperature is 180 degrees Fahrenheit. It is a UV post-cure. A fiber-filled polyamide material from 3D Systems, Duraform HST composite, exceeds a mineral-filled PA12 in all areas except tensile strength. It is similar to a 25% mineral-filled PA12. The fiber content increases strength, stiffness, and heat deflection temperatures to temperatures above 300 degrees Fahrenheit. It is a good choice for functional applications. The material is somewhat brittle, however, with an elongation at break of 4.5%. Newer versions of PEKK plastics are coming out in production-grade versions for laser sintering additive processes. These materials are being used in such applications as aerospace. PEKK CFHT23, for example, is one of the Monel group of nickel alloys. This thermoplastic is a high-temperature resistant polymer filled with 23% carbon fiber, which helps reduce directionally dependent strength, also known as anastrophe, of built parts. This gives you more flexibility in part orientation for the build. This material can be an alternative to aluminum. Metal additive systems like the EOS INT line can build with these materials, especially for applications in the aerospace and automotive industry. The polymer is semicrystalline and begins to soften and start to flow at 318 degrees Fahrenheit or 159 degrees Celsius, its glass transition temperature. It has good structural performance until it reaches temperatures in excess of 250 Fahrenheit or 121 Celsius. It also has good mechanical properties, chemical resistance, thermal stability, and flame retardance. And now for some of the newer metal materials. 3D Systems recently introduced its laser form materials for metal parts for the healthcare, aerospace, dental, and other applications. Laser form Ni625A is a nickel cobalt chrome material. It suits applications requiring high temperature, corrosion resistance, and high strength. It is for use with 3D Systems Pro X DMP 320 systems. Laserform COCRF75A is a cobalt chrome material for industrial parts that must resist corrosion, wear, and high temperatures. It is used to build medical tools and devices, dental implants and prostheses, molds and dies, high-temperature industrial applications, and parts requiring high temperature at elevated temperatures. It too is for use with the Pro X DMP 320 systems. Laserform 174PHA is a stainless steel material for parts that resist corrosion, exhibit high strength and toughness. Mechanical properties and corrosion resistance are maintained at temperatures up to 316 Celsius or 600 degrees Fahrenheit. Laserform ALSI10MGA is an aluminum material for parts that require lighter weights, good mechanical properties, and high thermal conductivity, particularly in industrial, automotive, and aerospace applications. It too works with the Pro X DMP 320 systems. Typically, when you think of metals and additive manufacturing, you think of some kind of laser sintering process. However, newer technologies, or more accurately, repurposing of additive technology, is enabling metal material to be used in extrusion and vat photopolymerization processes, more commonly known as FFF and stereolithography. Now, this slide shows what it looks like to have a stereolithography or vat photopolymerization process using plastics, but imagine using this with metal materials. Dutch 3D printing company Admatec has developed a metal slurry consisting of metal powder and binding agents that can be cured using this stereolithography-like process, but it's using digital light processing. The metals for this process include alumina, zirconia, and silica ceramics. Post-processing usually consists of debinding and sintering in some kind of a furnace, but the result is stress-free, high-density metals, somewhat similar to 316 stainless steel, and the layers have micron accuracy. One of the benefits of using a metal binder slurry is it resolves some of the safety issues commonly known or often known when using metal powders. Part finish is similar to other materials used in stereolithography processes. Markforged and Desktop Metal are two recent companies that focus on extruding metal. They have a way of combining metal powder with a binder that can be put into a form, such as a rod, which is softened enough to extrude. A second trend in materials involves strength. Here's a look at some of the latest materials with strength as their key feature. A recent addition coming soon from SABIC will be a high-impact strength polycarbonate. Parts made from this material were shown at RAPID. It will be available in filament form for fused deposition and modeling systems. This material will offer more impact resistance than other commercially available PC filaments and can be processed at standard PC conditions. Potential advantages include reduced part damage in secondary operations and higher levels of performance in end-use applications. SABIC also has a high-impact strength Ultem filament designed with the benefits of Ultem 9085 resin, but with greater toughness. Ascentium Materials is a company that makes materials for extrusion low-cost 3D printers. This company recently developed a process using carbon nanotubes and plasma to create strong 3D printed parts, parts that are equal in strength to those made from injection molding. According to the Ascentium engineers, it's the failure in the interlayer bonding of printed materials that limits some extrusion-based 3D printers from producing anything more rugged than trinkets and early design prototypes. Lots of extrusion materials deliver weak bonds between the printed layers, weak enough that under heat, tension, or z-directional force, the layers will start to peel apart. By combining electrically responsive nanoparticles and precision electromagnetic fields, the engineers increased z-directional strength, eliminating the interlayer bonding issue. The Ascentium material has a coat of carbon nanotube solution to illuminate the weak joints between print layers and electromagnetic fields while printing. The company's Fuse box works best with this proprietary carbon nanotube coated filament, flash fuse filament it's called, to create isotropic 3D printed parts. With these proprietary processes and materials, Ascentium claims that it can solve the z-directional strength issue, restoring up to 95% of the tensile strength of an injection molded piece. Some of the newer materials for the strength from EnvisionTech include epoxy, a partially biosourced, tough, dual-cure material that delivers strong, thin-walled final parts. Epoxy offers a good relationship between flexibility, hardness, and heat resistance that also suits connectors. It is compatible for use on the desktop and per factory machines. E-Modal Flex is a highly accurate modeling material with improved elongation at break that will be offered in both green and black. It is also compatible with the desktop, per factory, and 3SP EnvisionTech machines. Carbon has a unique programmable resin platform that delivers material durability and elastomeric responsiveness. One of the examples is the rigid polyurethane RPU. Stratasys recently introduced FDM Nylon 12CF. This is a carbon fiber-filled thermoplastic strong enough to replace metal components in a range of applications. It can be used for rapid prototyping, strong, lightweight tooling, and end-use parts. It contains 35% chopped carbon fiber by weight, so it has a good stiffness-to-weight ratio, which meets functional performance testing demands in automotive, aerospace, recreational goods, and industrial manufacturing sectors. It is expected to ship in the second quarter of this year. FDM Nylon 12CF is available for the Stratasys Fortis 450 MC Production 3D printer and is compatible with soluble support SR1110. It does require an updated version of Insight software and a hardware upgrade. This material can produce parts in a layer thickness of 0.0110 inches or 0.254 millimeters. The medical industry is becoming a very large market for 3D printing additive manufacturing. For example, 3D Systems recently introduced its VisiJet M2R TN for its ProJet MJP 2500 Plus system. This material is a rigid dental model material in tan, the most common color for dental models. Covestro has been involved in materials for additive manufacturing for a while, but as additive gains greater importance, the company has decided to come forward a bit more. So it brings new material options based on its polyurethane and polycarbonate filament technologies for applications in medical as well as other areas. The company is developing new products specifically tuned to offer increased levels of performance for industrial 3D printing. EnvisionTech recently introduced a number of materials for the medical market. One of them is silicone TG, a technical-grade silicone for building soft implant surgical models, such as noses and breasts at room temperature. This RTV1 silicone, available in transparent, black, or in shades of gray, will cure by itself within a few hours under the influence of atmospheric moisture. It displays low shrinkage, a medium hardness of about 20 Shore, and is odorless during printing. It's suitable for relatively large parts made on EnvisionTech's 3D bioplotter. PCL45KRG is a research-grade polycaprolactone for tissue engineering applications. Mechanical stability of the PCL objects are controlled by the porosity design of the part. This material can be used to help spur bone and cartilage regeneration and is even useful for drug delivery. The surface erosion of the material allows controlled release of additives during the 1 to 3 year degradation period of the fabricated parts. LG Support RG is a low-temperature research-grade saccharide material derived from cellulose that is used for sacrificial supports. It can be processed as a hydrogel and dissolved in distilled water after the support for the 3D build project is no longer needed. Biocompatible and self-friendly, this material does not negatively affect a final object's biological properties. Processing temperature is 23 degrees Celsius. And those are just a few of the materials that have been introduced so far in 2017. More are definitely on the way as this area continues to grow. This webinar will be available at our online website, designworldonline.com, and a copy will be mailed to those who registered. You can tweet anything about this webinar at #DWWebinar. You can also connect with Design World on any of the social media platforms that you see in front of you. And if you would like to further discuss this webinar, you can do so on engineeringexchange.com. Thank you for being here. And again, thank you for attending the webinar, and we hope you have a great rest of your day.